So hello everyone, I'm Kris, and I'm here to talk about dependency injection and bust some of the most common myths about it. So I strongly believe that this design pattern, which is very common in other languages, especially object-oriented patterns, but design languages, but not only, it's often misunderstood and misused in C++. So I'll try to discuss the benefits of it and potential use cases for it. It's actually a case study, so we'll take a look into that. So it's actually so misunderstood that, sorry for that, but I have to clarify that this talk is not about CMake or dependency management. So just without further ado, let's begin. So what's the motivation and goal for this talk? It's basically to increase the number of attendees, developers in C++ who are willing to use and try DI, assuming that not everyone is using DI, which is the shortcut for dependency injection. So let's assume that there is a talk about DI at CP now. Well, it's actually happening as we speak. And there's a number of attendees greater than 0. Assuming the speaker is an attendee, I checked that already. But thank you for coming either way. And there are attendees who are not using DI, or not, have bad experience with DI, don't know what is DI. Yeah, half of the audience. The attendees who are thinking that this talk is still about CMake? No. That's good. OK, so the talk has been given by the speaker, so it's happening. That's the word. So the final goal is that the number of attendees, you guys and girls, and attendees and developers all around the world will be more willing to use DI afterwards. So that's the goal. Let's keep that in mind. We'll see how it will go. I will try to convince you that DI is not that scary. It's quite useful if applied correctly, though. OK. So quick agenda outline. In order to talk about DI, we'll have to talk about design a bit, because it's kind of related. It's design patterns and all this stuff. So we'll talk briefly about principles, just to introduce the DI. We'll do the discovery of the best way of implementing this requirement, which is how to increase the number of developers using DI. So we'll talk about dependency injection in that context. And then we'll talk about other libraries, well, C++ libraries, which can simplify some of the things which will be introduced by DI. I don't want to go too much ahead, but we'll talk about some of them. So one of them will be Hyperdemic, Google Fruit, and BoostDI. And we'll sum up afterwards. I'll have a lot of points and a lot of slides. Sorry about that. I'll try to go quicker through some of them. Some of them I'll try to dig in a bit more. But if anything, I would like you to remember everything which is dark blue, which has dark blue background, because that's what I found in years of using DI and seeing how it's used. The most important part to know. Make sense? OK. So briefly about design principles. We won't spend a lot of time on that. So the only way to go fast is to go well. That's a quote from Uncle Bob, which I think is really important when you think about the good design patterns. Has everyone read that book? If no, I really encourage you, because it's a very good read for improving your software design skills. So yeah, really encourage that. It's not related to, it's in Java, but it's like language agnostic. So when I talk about design, I will have 3 main concepts in mind. The first one being it has to be flexible, because nothing in software development is actually certain besides the bugs. I guess the bugs are quite certain, everyone is doing them. And that the requirements will change, because all the stakeholders will always change the requirements. Even if you set in stone what you have to do, at some point you'll have to change that. So that's certain. Also, we'll talk about being it scalable. So easy to extend, maintain, and reuse. Therefore, we'll talk about DI, because that's the reason we would use it. And we'll talk here about large scale development, which is like kind of like Google scale, where there's like hundreds of millions of lines of code. And so that's, for example, how it looks. And I actually talked to Titus Winters from Google, and because Google doesn't apply the dependency injection, they didn't start from it. But his point was that if they had a good framework and they would start from scratch, they would actually consider it as a valid point to do the software development. So I think that shows a lot, but it's obviously case by case. And the last but not least, testable. We always should put test if you like the code we actually have. So it's the Beyond Zero also from Google, so it's really important to remember about it. Make sense? So the last remark, it's like clean code defines the solid principles, but they are also, on the other spectrum, stupid principles, which we don't want to follow. We want to be on the left side here. Sometimes we get to the right side, but we don't want to be there. So I'll try to focus on the highlighted part, which is underlined, the single responsibility, dependency injection, and kind of bust the right one, which we don't want to really have. Okay, so having the principles in mind, let's dig into find the best way to implement this requirement which we introduced in the beginning. And we want to focus on those guys. So at first, we can keep it simple, stupid. So as I pointed out, stupid is something which we want to avoid. So if we approach it from very simple kind of scripting language perspective, we won't get too far, in my opinion. So the easiest way to kind of implement it is to have like some main function and global functions being used in there, and just ask the attendees before and after the talk, and if the number of attendees willing to use DI has increased, that's great. Otherwise, not so much. But but we have to always remember that code is much often read when it's actually been written. So we don't write that much code as we read. So I pointed out things scale. So that's like a really simple example because it's presentation and we have some limited space on the slides. But imagine that we have hundreds of thousands of lines of code of that, and dealing with that, we don't want that. So I consider that stupid, not very simple. Is that code flexible? Well, not really. It's tightly coupled. Is the term which we'll use very often here. Is it scalable? Not really. It's really hard to extend. Imagine that you have thousands of lines of code, one function main, and try to add something to it. Well, good luck. Is it testable? Well, not really either, because it's all in main. It's not testable from C++ kind of perspective. You would have to go to like some scripting. It's a mess. It will be difficult. So the first thing, let's make it somewhat testable. I mean somewhat because it won't be perfect. And by that I'll be talking about behavior-driven development, which is like BDD. Just a small remark. How we can do that? We can just implement the steps for the requirement we had. So assuming there is a talk, so we have one class already, which is a CP_now talk, which is a system under test, and that the talk has been given. So we kind of run whatever. Then the result of it, which is the result that the number of attendees has increased, willing to use DI. So yeah, that's already better than before, right? Because we can test it in C++ using some kind of framework. That's not really important, but it's already better. So in order to do so, we refactor it a bit. So right now, we just, instead of main, we have a class which has the run function, and the implementation is still there. So you can imagine that we have one class and thousands of lines of code into the run function. It's a step, in my opinion, in the right direction, but it's not really a big step, a small step. So, the first good thing about it is that we should consider test driving the code because, well, it put us in the right direction of the design we will have. And just to talk about the BDD and TDD, the difference here is the fact that the BDD is the thing which, tell us how to build the right thing, but it doesn't tell us how to build it right. So that's TDD. So you can still have BDD, let's say, end-to-end tests and thousands of lines of code into this one function. And that's BDD because we have all the requirements satisfied. But since we didn't follow TDD, it's not really right because it's coupled and it's hard to extend. So following on that, let's make it more flexible. In order to do that, let's introduce single responsibility principle. Is everyone following it? Yeah, most of the audience. So quickly about it. It's basically that a class should have only one reason to change. Otherwise, it's doing too much. It's too difficult to reason about it, and it's a mess, hard to test, tightly coupled. So if we follow to our example, we have a speaker, and the responsibility of the speaker will be to give a talk, let's say. As you can see, it's still tightly coupled here, but it's still, because the Kris is coupled to the speaker, the name, but we'll get into that a bit later. But the idea is that there's one responsibility. There's no other stuff about, like attendees who, supposed to attend and participate and maybe ask questions or whatever. So we have these responsibilities, which is better than just have one CEP now talk, right? Because we can test them somewhat in isolation. So speaker and attendees can be tested in isolation. What about CEP now talk? Well, we'll kind of couple them to the talk. So we'll have the member variables, and then we'll just run. So here we still don't use dependency injection. We have member variables which are coupled to the CEP now talk, but the design is still better than before because we can test speaker and attendees in isolation. However, the CEP now talk has to be tested as a whole. So when we test the CEP now talk, we'll test the speaker and attendees as well, which is not ideal from TDD perspective, but it's okay from overall design at that point. So is that code flexible? Well, it's more flexible than it was before, but it's still tightly coupled because speaker and attendees were coupled to the talk. Is it scalable? Not really, because we often have to repeat ourselves because the Kris was coupled to the speaker. So if you have different speaker, we have to create different class. Is it testable? It's sort of testable, but it's not ideal because we can test speaker and attendees in isolation, but we can't test CEP now talk using fakes, for example. So somewhat better, but it's not ideal. But we still want to follow the rule because it's good from the design perspective because it gives us better isolation, and all in all, it's better than having just one class, right? But what about this coupling? And that's where actually dependency injection can be introduced, I think, as a first step. So it's often, this scary term, as I said. A lot of people feel like it's CMake kind of thing or whatever, but it's not. It's quite simple, and that's the, dark blue background. So if anything, remember that slide, at least. So from the design perspective, DI is just about reducing the coupling. The less coupling, the better from the software development. So that's the way of doing it. But what is from the C++ perspective? It's actually just constructors. If you use constructors, you most likely use dependency injection. Woohoo, that's all. Thank you for the talk. It's a very simplified version because whether you use DI correctly depends on what and how what you will pass into those constructors. You can totally screw it up very easily. DI has a lot of gotchas which we will try to show and avoid. Make sense? And very important, DI doesn't imply a library or framework. It's very common, confused that containers, like DI containers, they coupled to DI, like dependency inversion principle and stuff. No, that's not true at all. You can do DI without any libraries, frameworks whatsoever. It's just manual DI. There are benefits of using frameworks, which we will discuss, but it's not really the requirement of having it. So let's revise again. We have this tightly capping, no DI, CP now talk. That's not perfect. How we can, introduce a better design? Let's start from a simple one. Name. Let's decouple the name. Instead of having it coupled to Kris, let's add a constructor. Yeah, the DI for you. In all glory. Very simple. We have speaker which takes the name as a parameter. Very simple approach, but changes everything. It's actually a very powerful concept. So what about the talk? So here, just a two slides ago, that was tightly coupled because we didn't have the constructor. But if you introduce a constructor, at least we can decouple them somewhat. We still use single responsibility principle, and we don't depend on abstractions, which we'll get to. But it's still better because speaker right now, and the name of it, it's decoupled. Make sense? So DI is often, referred to a Hollywood principle. Don't call us, we'll call you. So it means we inject stuff instead of asking for stuff, which is always better, always. But when we have DI, we introduce this wiring thing, which we will talk and discuss what it is in a sec. But it basically, we kind of move the idea of constructing things inside the class outside, so that we move that responsibility, not to deal with it, kind of move the problem outside. But you can see that like speaker and entities will be created outside, and then we can inject them. Inject is like pass them to the constructor. There's no magic into that. So wiring, yet another thing to remember, separates the creation logic from the business logic. So we don't want any raw, make unique, new, any of these goodies in the business logic, because that's where the logic sits and where the creation of all our objects sits. It's totally different place, and that's the wiring place. Wiring has negatives as well, but for now, I think wiring is like the step into right direction if it comes to design. And regarding to that, the composition root, which is kind of similar to the wiring thing, is a unique location in application where the modules are composed together. So preferably in your application, you would like to have the main, short main, basically, which constructs everything, and after that you just run the application. So that's the perfect design from DI perspective. And I think it's like really good software development practice because you can easily change the wiring for the production, for the testing, and everything is in isolation, easy to extend and flexible. So if you have something like the following, that in the run call, we create the attendees, that's bad. If we create them like that partially, like speaker is created in the main, but attendees are created in the run, that's bad. Good is pass the speaker and attendees to the track. So we get the immediate benefit of using the DI this way. We can, for example, create 2 different tracks and run them in parallel, for example. A very simple immediate benefit, which is already better because our design without any changes is less coupled to implementation. But there are tons of gotchas with DI, which we'll discuss right now. So the first one is not using constructor consistently. So for example, if you have a speaker, and speaker actually has a constructor, but we don't pass the speaker via cp_now_talk, then we introduce this coupling again. So let's not do that. Let's pass the speaker into the talk instead. So we wanna always be consistent about passing it. When we started from it, let's do it all together. So that's bad, but that's good. So that's coupling and that's not coupling. That's the difference. Singletons, yeah, singletons are always bad. Basically, they are really difficult to test, difficult to fake. So we don't really want to see code like that when we have like speakers, instance, get, blah blah blah, Kris, talk. It's really difficult to test, and that's not really a good design. The only way you can use singletons is if you inject them via the constructor, because then you can fake them and deal with them somehow. It's still not ideal, but if you really want to follow them, go for it and just inject them. Just don't do that, because that's really coupling our implementation, and it's really hard to test. You have to do like linking magic or something to make it happen. Make sense? So yeah, as a rule of thumb, let's avoid them. So that's bad, but that's good. So as I pointed out, when we inject stuff, it's always good, because we can reason about it. One of the most important mistakes and gotchas which I found is being made when using DI it's called carrying dependencies, in which when we have the talk and we have the speaker which takes the name, that it's still maybe not coupled. Maybe we'll pass the speaker as the constructor, but no. What we'll do, we'll pass the name instead. We'll pass the name to the talk, and the name after that will be passed to the speaker. Well, that's bad because that's a leaky abstraction, and that's, maybe in this silly example it's not terrible, but imagine that pass through all the members to all your other dependencies you have. That's very difficult to test. That's not a good design, and I bet it's very common, and you see that you pass in something which you don't use just to pass around to the dependencies they may use that. That's not a good design. That's asking for troubles in the future. So yeah, important one, because very common misused. Let's pass the objects instead of dependencies which are required by the underlying objects, because that's not good. So that's bad, but that's good. Passing speaker is always good. Passing the name and through the talk, that's not a good design. We can also do it a bit worse with inheritance. It's kind of the similar case, but it's often very common in Java that you pass. In Java you can't do multiple inheritance from the interfaces, but like in C++ you can. So you can imagine that you can inherit from speaker and attendees. Exploit their APIs, but that's good. That's bad. That's always bad because we have the same problem because, for example, we will pass the name to the speaker. We could pass the speaker here and copy it to the inheritance derived class, but the problem is that we still rely and couple to the speaker because of the API of the speaker. So we don't want to do that, and especially we don't want to collide with attendees if they have the same interface. So let's not follow that. And as a thumb rule, we always prefer composition over inheritance. So that's bad because we coupled. That's good because we less coupled. Yet another thing is when you talk to your distance friend, it's a good advice from Uncle Bob not to talk to them. You only want to talk to your family, basically. keep it close and tight. So for example, a bad idea would be if our speaker will get the manager, and manager, will get the speakers, and we get. If you have a lot of dots in your code, it means you're doing something wrong with the design, because that will make your code extremely difficult to test, because you will have to fake multiple, chains in order to get to the final thing. So distance friends, not good. Don't talk to them. So let's just talk to the immediate friends, which means that let's pass what we need for that object by the constructor. It's called also the law of the matter. It's a principal guideline. So that's bad, but that's good. So let's follow that one. Yet another one is not using strong types. As you probably know, it's like that will be a weak API, because we can easily mistake the order, and it will compile. It will sort of work, but it won't do what you need. So not best. And there's a really good talk by Jonathan, which I would advise to watch if you haven't, about the strong types for the strong interfaces. So we can introduce like a named parameters, and named parameters are really good with the DI, because it's like you can inject specific things to specific constructors very easily with that. So the strong API, first name, last name being a types instead of the names. It's like even if you have the header and and the implementation, the names don't matter. So in C++, so you can screw up the names and get really confusing error messages sometimes if you don't test it. And much better would be to have the first name and the last name. That would be OK, and that would be a compile error. So that's great. And you can also find that designated initializer in C++20 may fix that problem. However, you can misuse them as well if you use aggregate initialization instead. So it's not a silver bullet. So let's consider using strong types, because they improve our design. So yeah, so that's bad. That's good, because we have we have the types instead of the names. OK, so moving on. Let's make it even more flexible so far, because right now it's like single responsibility give us quite a bit, but it didn't give us too much, because we couldn't easily fake it. We couldn't test it. We kind of were coupled to specific types of the speakers and attendees, and that's not extremely good from the design perspective, because if you want to extend it, it's not really that easy. So is everyone familiar with dependency inversion principle? Most of you guys, some of. So basically, there are two things about the higher level modules and low level modules, but the main idea is that we should depend on abstractions and not the implementations. So we don't want to depend on the concrete implementation of the speaker and the attendees. Instead, we would like to depend on abstractions. So that kind of leads us to make sense. It's kind of a good rule of thumb, because we can then fake it and test it. We can easily switch it. It's like we won't have just one type of speaker, right? There will be like boring speaker, keynote speaker, regular speaker, and so on. But that leads us to polymorphism. And in C++, there are tons of ways of doing it. It's like in Java, we'll just say, I don't know, inheritance, whatever, interfaces. But in C++, we have like inheritance, like object-oriented design. We have type erasure. We have variants, templates, concepts, and so on. So there are a lot of ways of achieving DI, which is passing the right things to the constructors. So let's take a look quickly into them. The first one, the most obvious, will be object-oriented design in C++. We have this virtual function, virtual abstract class with, we can put constructor on it these days, maybe in some compilers. Sometimes works. Which is basically an interface, right? Everyone knows about it. It's always important to remember that we need to put this virtual destructor but oh well, that's the thing. And then we can just have the regular speaker and just override the talk function. It's important to understand that it's actually introduced coupling because we can't use the regular speaker without this interface. So there's a small coupling with the interface and the implementation, which is not ideal, and we'll try to remove that at some point. So then we have to go to the heap. We introduce the smart pointers and all these goodies, I'd say. And our constructor changed a bit. We have, speaker-like, attendee-like. We move it or copy it, whatsoever. And our wiring, so that will be the common theme. We make, unique, make, shared, and pass it through. And we just run it. So it's basically as before, but we're less coupled right now. So that's good because right now we can actually introduce fakes or different types of speakers. So the design has improved. But, inheritance is the base class of evil, so let's not do that. You don't have to, take my word for that. You just watch that talk, and I guess you'll be convinced by Sean. So let's not consider using inheritance for dynamic polymorphic. That's like a rule of thumb for the good design. Let's use, for example, type erasure instead. We can use the simplest way of using type erasure in C++ would be just std function. And instead of having classes, we'll have just functions and lambdas. And it's basically the same idea. We have a function for the speaker talk. We have a function for CP_now talk, and so on. So that's kind of a common theme as well, that is like DI is only object-oriented related, but that's not true. We can use DI with functions. We can use DI with templates, and we'll take a look into that as well. Just to remember that it's not always true. And one of my favorite talks about functional programming is by Scott. And he actually described the solid principles from functional perspective. So object-oriented patterns is like there are a lot of names. There are quite a few good ones, which we talk about. Singular responsibility principle. Well, equivalent in functional programming. Well, a function. Dependency injection principle, also a function. Everything is a function because it's a functional programming. So we can follow that approach as well. So, and we can do the DI with it as well, because function, we can inject another functions and parameters into functions. So it's still DI. The constructor here is kind of the function parameters. And we can use like bind and pass some parameters into that and call yet another function out of it. So there are options here. And the wiring here will be when we have the talk, we kind of bind the names, and then we can call the talk without explicitly call the members, names. So it's basically like having a class with the member variables or something and pass them through. And ask will just call the other function. The track will call one of those functions. It's basically the same idea, just with functions. And that might be done with DI as well. So that's still DI. We can also follow type erasure in general. And type erasure, the idea is that we won't have the inheritance here. So we're not coupled to the interface anymore, which is good because not having this coupling is better. Less coupling is always better than more coupling. So having that, we can use, for example, virtual concepts. That's just the idea from a proposal a few years ago, which probably never happens. But I just liked it. So virtual concept is basically the idea that we have the type erasure thing, which is just a pointer to a function and void star to keep the data in it, like a std function does, and being able to use concept syntax to define the function signatures. But the idea is very simple, that we have the virtual instead of interface just for the members, and that would do the type erasure behind the scenes. That's not very important for that talk. The idea is that we can do the type erasure somehow. And then we pass the type erased thing into the constructors because we follow DI. So that's pretty cool. And then we do the wiring. as before, basically. We always have to tweak it a bit because it's wiring, so we have to, tweak the constructor parameters if the order is different or the types are different, whatever. But it's always the case. I'm pointing this wiring because that'll be an important thing in the end. And that's not C++. Variant, we can use variant. We can have the same speaker without the inheritance. Great, we can reuse that. And then we have the variant from all the possibilities which we can have for the speakers. So this principle is kind of closed for fakes, unless you add any, for example. I don't know. You can do some things with variant, but in principle, it's quite difficult to extend. But the idea is the same. We pass it through constructor. That's the main theme, if you haven't noticed so far. And the wiring, a bit different as before, but we pass everything through main. We create the track, and we run it. We can also try to do more, compile time approach. Kind of, if you care about the performance, as we do. And we can follow design by introspection. Is anyone familiar with that guy? Not a lot of people. I really advise everyone from who cares about the performance in C++ to follow Andre ideas, because it's kind of the evolution of policy by design. Yeah, it's really positive from the design perspective at compile time. But we can follow, for example, static polymorphism and just templates. We still have the speaker, not inherit from anything. It's the same as before. Nothing new. And then we just have the templates. But the important part is that we still have the constructor. So in the policy design, we would inherit from these guys and call private functions or whatever. But that's kind of not that flexible from DI perspective. So it's better from that design just to use the speaker and attendees as a templates which are injected by the constructor, because it's DI. We care about these constructors. And the wiring, as before, blah blah. We can use the deduction guides, or we can just pass through the types. A bit different than before, but very similar. And most dependencies are now at compile time. And we don't want to pay for what we don't use either way. So might be a good idea. Yet another approach, concepts. Everyone familiar with concepts? A lot of people are, maybe not that many. The idea is that we have these, kind of an interface for types, so we'll get better error messages, faster compilation times, and better description of what our types are doing. So instead of getting like error message from your library code, we'll get it at the point of the instantiation instead, which is always good because we don't want to expose our hacks in the library for the users. So that would be it's kind of the similar as object-oriented interface for the speaker before. So the implementation of the speaker will be basically the same as before, just no inheritance, because we don't have to inherit from concept. That's why it's much better than the inheritance on its own, because we're not coupling to the speaker-like kind of thing. So that's positive. But yeah, so the point is that it's the same as with type erasure templates. And yeah, all in all, that's very positive from our perspective. Make sense? So concept in 20, instead of having the type name or a class, we'll just put the template through it, the concept. So the speaker-like and the attendee-like are concepts. We can also use the requires clause afterwards, and that's not really important, but the idea is that the type name itself will be a concept that will be verified at that time. So how that will be related to DI? When you have the talk, we still have the speaker and attendees being templates, which have to be constrained by the speaker and attendee-like kind of things. And after that, we pass them through constructors. Nothing new, right? So the only difference between the templates and concepts is the fact that the latter will verify the interface at the point of instantiation, and the former wouldn't. So we would get, if you use the speaker thing in the run function, and it doesn't have the talk function implemented, then from the templates perspective, you would get a nasty error message from the run call that, oh, well, you don't have this function, I don't know what to do with it. And from templates perspective, we would get it when we instantiate the CVNow talk that, well, the speaker which you passed through as a type doesn't satisfy this interface. Make sense? It's a positive thing, so when you get your hands on concepts, apply them, because it's better than just the types. So what about the wiring of it? It's basically the same as before. We have the speaker, which we have to, create. And you notice here that like the speaker-like, it's a concept. So before we would say auto, and auto is considered like the weakest concept you can have, which doesn't have any requirements. And the speaker-like would be a concept which has to have the talk method available for us. So it's, being explicit is usually better than being implicit. So that's a good thing as well. And then it's the same for the attendees. And we create both of them, and after that we create the talk, we pass them through as always, and we run it. There's a question?
Aren't you now creating some coupling here? If you just made auto speaker and auto attendees, the only place where that matters is in CVNow talk.
So the question is whether we create some coupling by using concepts here. So the speaker-like is anything which will be constrained by the speaker-like concept, which is just the talk call, like requires the talk method, right? So anything like regular speaker will be satisfied by that concept, and keynote speaker will also be satisfied by that concept because it has the talk member call, right?
True, but there's no reason to couple it there. CVNow line 3 will get everything for you.
Could you repeat?
The auto track equals CVNow talk will make sure that the concept requirements are satisfied.
All right. Yeah, I agree. So the observation here is that if you use, sorry, it's like I didn't get it before. If we don't follow always auto kind of thing, when the constraint will be verified here, but it also be verified here if you put the speaker-like on it up front. If you put auto in it, it won't be verified there because it will be anything, and it will be verified later on. Whether that's a good or bad, I wouldn't say that's coupling. But yeah, it's like, would you always put auto on your initialization members, or not? Yeah, it's like some people prefer. It's a kind of like a style thing, I'd say. I would feel like having a concept is better than not having a concept there, because when we put auto, it might be anything, and people complain that it's often I don't know what it is, right? It's not coupled at all to anything you passed, but people don't understand what it is, and they complain that, well, I don't know what it is, and I prefer to put a concrete type on it, right? But then it's just this type which you can create. With concept, the situation is a bit better because it's like an interface, abstraction, which it's not a concrete implementation, but it's something which satisfies that interface, which is just the talk. So I guess there are pros and cons. I do not disagree that it's a bit of coupling, but I also see the positives of using it that way. Sorry, I can't give you any better answer. When that, unless anyone else have thoughts about, should we put the concept name on it, or it's better to put author, or even regular speaker on it? Maybe we can vote. Who is for author? No one. Okay. Oh, there's one person. Who is for a concept? Okay. I would say half the audience, I guess. And who is for the third option, the regular speaker instead? Okay, there are some guys. Why? Why would you use that? That's coupling. That's coupling. No, I'm just joking. I see the positives and negatives of all the approaches. So just to the listeners, the overwhelming number of audience says concepts are the best. Moving on. So let's try to make it testable. So our design is flexible, scalable, it's awesome. But is it testable? Well, we can actually do TDD, test-driven development, with dependency inversion quite well, which is quite decent. So let's assume we have a test. It's like simple testing framework here. And usually when you write a test, that's like maybe advice on the side, but I think it's important to follow that. You usually want to start from the expectations. You don't want to start from creating, what I want to test. It's how I want to test. You want to, say what I want to test. So I want the track run, which returns the true if that's from the test, right? Should return true. Should return true if the number of attendees who are willing to use DI increases. So I want to expect that. I don't want to focus on how to do it. That's the first thought in mind when I follow TDD. It's like, oh, I want to test that guy. And then, it's like if you use mocks, fakes, whatever approach we have for testing. For example, we can use, Google mock, or if you use inheritance, or we can use fakes. If you use typebreaker, there are options here. I just, pointed out the simple example when we use expect calls on our guys. And then that's the wiring part, which we talked through a bit. So we have to create the fake speaker, fake attendee, and the track. So fake speaker and fake attendee might be mocks, might be stubs, might be fakes. There are tons of options, and really strong opinions about what's the best. So I don't want to get into that. Basically, it depends on whether you want to do it at runtime, compile time, and overall whether you are object-oriented guy or not. But there are pros and cons of any solution, I would assume. But it's important out of maybe this slide that test-driven development is good. And if you follow it, you'll have a good design, which is testable and which will most likely follow DI, because it's like I'm saying less coupling is better, but TDD is kind of coupled to dependency inversion. So maybe sometimes coupling is good, but yeah, in general, in design is not. So following the dependency injection principle, is it flexible? I would say yes, it's loosely coupled because we are not coupled to the specific implementations. We're not saying the speaker is just the speaker or Kris. It's any kind of speaker we want. The only requirement is that it has to satisfy the talk number call. So that's good. We want that because then if our product owner will come and say, I want this awesome speaker right now. It's like, can you implement that, Kris? It's like, I'll say, sure, I can do that. And I don't have to change, and I can implement that guy, an awesome guy. I can test him in isolation, and I don't have to change any of the main logic, business logic, or anything like that, because I'm loosely coupled. So it's good. Otherwise, I would have to change the implementation inside and just deal with it. And that's not what we want, because it's not flexible and really hard to maintain. Is it scalable? Well, I would say no, because of this wiring thing, which I kind of pointed a few times about. I believe that the wiring makes it really not scalable. So if you think really huge scale, like Google scale, and we have to create millions or thousands of classes, well, manual dependency is kind of difficult, because the order is important, and we'll take a look into that in a few slides. But for now, it's a question mark, and I would say no. You can disagree, or you can even destroy me after the talk, maybe. But yeah, definitely something to consider. Is it testable? I would say yes. It's much more testable than before, right? We can test the speaker in isolation. As I pointed out, if we add a new speaker, we can test it in isolation. And we can test the talk. That's something new, because we can test the talk by passing the fakes, as we pointed out, and test the calls and make the corner cases testable as well, because it's like if we couple ourselves to the specific implementations, then when we test from the end-to-end kind of integration test perspective, it's extremely difficult to get to the corner cases, and that's what unit testing is about: the corner cases, the documentation, and finding bugs easily. Because if you follow just the BDD kind of end-to-end testing, then when we have a bug and it doesn't work, well, good luck if you have really huge coupling, and trying to find the bugs is really, really difficult. And unit testing is really helping with that. And you will have a good design if you follow TD either way, so that's always good. So as a good practice, I would say considering proper abstractions for your project, it's a good thing. So for example, templates, concepts, if you know the dependency at compile time, just go for it. It's like it's C++. That's what we care about, right? No overhead. Zero overhead abstractions are always good, and following them, it's a benefit from the performance perspective. It might not be a benefit from compile time perspective or reading perspective, but it's also C++. You deal with it as you can. Type erasure. I would say if you have a runtime dependency, just go for type erasure. Either std function or like in-place function is actually better, because it lets you control the small buffer optimization, and std function not as much. So performance-wise, it would be worse, and it reduces a lot of code bloat. But it's still better than inheritance, in my opinion. So for type erasure, for runtime dependency, I would go for type erasure. And inheritance, well, although we have all these cons expert right now, and it might be devirtualized in some compilers sometimes, I would say never. But that's just my opinion. So who listen to me, right? I would prefer those guys before I would ever go to the inheritance, either way. But it's, as usual, there are pros and cons of any approach, and I bet there are people who would say that inheritance is good, and they would have good reasons for that. I'm not arguing with that. It's just personal opinion that I would never go for it, and I have my reasons. So all of that, it's so far, I guess, fine and dandy. We have better design than we had in the beginning, so the talk is going in the right direction, in my opinion. But we have a problem. I think we have a problem. I don't know whether you have a problem, but I see that all these solutions have one thing in common, which I tried to point out a lot of times. Any ideas what that would be? Yeah?
Dependencies are often in implementation detail that the client should be wondering
The dependencies are
Often in implementation, you tell the client of that thing that's injecting dependencies shouldn't know anything about it.
right. So the observation, which is not what I'm looking for, but is that the client shouldn't know about some of the dependencies. But yeah, that's a valid observation.
And worse, the dependencies.
You're right.
It's just
However, if we depend on the abstractions, we kind of decouple ourselves from that, right? Yes, somewhat. Any?
I would say the wiring, but
Oh, I like that.
yeah.
So
I'm efficient for that.
yeah. There's like yeah. So a lot of people mention about the wiring. A good audience. Now, so the idea is that the manual wiring which we had, and that's what I'm trying to point out. And it's like I'm not saying that observation which was pointed out before is bad or something. I just want to focus on that because I'm thinking like going to the
Well, effectively, it's related because
Right.
injecting that is the point where you're doing the wiring.
Yeah.
It means that you have to know
right.
many layers.
Yeah. The observation is that it's related. I really like this observation. So yeah, the manual wiring is the fact that we have to we kind of move this problem from having it inside the classes to outside the classes, and right now we have to create all those guys and pass them through, which is tedious, not the it's not the best usage of the developers' time, because developers want to focus on the business logic, not on the wiring. Wiring is boring, right? Who want to create classes? It's the same with the functions. It's the same with the templates. It's the same with the concepts. We always have to do that, and it's not ideal. It's not that And again, thinking large scale. Imagine that we have hundreds of thousands classes which we have to create, and someone has to maintain that code. So we're saying it's like DI is so cool, but it's like, oh my gosh, no way. So we kind of introduce it's called the wiring mess. And that's like an example of it. When we have, it's just go forever, right? It will have like so many of those classes which are different in production, which are different when the logger is enabled. Oh my gosh, and you know what I mean probably. So it's boilerplate and tedious. It's hard to maintain because order is important. So if you switch the order of the constructor pointers, you would have to switch something in the wiring. Not great. Could be better. And we have multiple configurations usually for the release, for the debug. All of that makes it like not something which most developers would enjoy. So to remember, the wiring mess is something which we don't want to have. And how do we get there? We have this single responsibility, which introduces a lot of classes, right? Single responsibility, like tons of classes. Everyone's seen that. When we open the IDE, and it's like we can't see how many classes there are. After that, we introduce the dependency inversion and injection. So we pass them through the constructors. Great. And we introduced the wiring mess after that because the main was like huge, bigger and bigger. The more dependencies we had. So all of that get after a while hard to maintain, and we have deadlines as always. At some point we have the pressure, and what we do hacks and workarounds. So we break the single responsibility, we break the dependency inversion, and all this DI goodness and constructors and all these ideas just gone away, and we actually end up with a worse code than before because we kind of follow the DI up to some point, and we stopped after a while, and we have this, the worst solutions are the halfway solutions. Like for example, when you switch to different unit testing framework and you switch it halfway, you don't want to just deal with that. And that's what we don't want to deal with when we use the DI as well. So, but there is a solution, there is hope. There are always frameworks which always may help. So the main idea for the frameworks, and as I pointed out before, is like frameworks are not required for DI. We can deal with DI without the frameworks. It's totally fine. We just have to deal with this wiring mess, and it's totally fine just to deal with it. In the small applications, it's probably even easier sometimes, but in the large scale, thousands of classes or even hundreds, it may become difficult at some point. So the idea is that if you have a good framework or a framework which can remove the wiring mess for us, that will be better. Well, let's check it out. So are there any questions related to the design which we have so far? Nope. So let's move. So there are tons of solutions for DI libraries in other languages, and there are some in C++ as well. They often called also the inversion of control containers. Just to point that out, it's not really important. So the goal of them is to remove the boilerplate code, the wiring mess. That's the goal. So all this, creation of the objects and passing them through, moving them, passing them, make shared, all of that. Let's just, remove that. And we can do that by, frameworks do that by, being able to deduce the constructor parameters, deduce the object lifetime, and create the object graph for you. So we'll take a look into that, how that works. But all in all, writing DI library is not easy in C++. I can tell you that because I wrote one. There's no reflection, so it's hard to deduce the constructor parameters. You have to do a lot of TMP magic to make that happen, but it's possible. We have all these R value, L values, passing by the constructor, which is like, oh my gosh, what to do with that? So you have to have the object lifetime dependencies, get right. You have east const, west const. DI has to handle that. And actually, it cannot care about it. Error reporting is like, usually we create the objects, so we deal with the constructors because DI is about constructors. And that's the worst part if it comes to the error reporting because it's a constructor, so it's harder to use like expect or something like that. Usually we end up with expect exceptions or other problems. And we don't want to pay for what we do not use, right? So it's basically how to make that happen. All of that is like kind of difficult. And there are other problems. So there are a few approaches, at least a few approaches which I've seen. So compile time, that's I think is like preferable for all C++ code when we get the compile time error. So if all our dependencies are not creatable, if you cannot create the CP now talk, we will just get a compile error. Yeah, that would be great. There's kind of a runtime compile time when we get the compile time error, but the backend is kind of runtime. So sometimes we get exceptions, sometimes we don't. And fully runtime when we have like the XML kind of Java approach when we read from the XML and we can create objects, or when if you don't have object being bound, we get exception and deal with it in production if you don't test it. But preferably we would like compile time errors, I guess. So overview. There are a few libraries. The first one is Hyperdemic. Anyone familiar with that guy? There's one person. So it's header only. It requires STL and boost. It's 11, and it's runtime. So we'll take a look into that. There's Google Fruit. Anyone familiar with that guy? No one. It's not people from Google, I guess. It's a library. It has Google license, whatever. It requires STL, boost is optional. And it's this semi-compile time approach, which is, you get some errors at compile time, some at runtime. And there's mine library. Anyone familiar with that guy? Yeah, everyone, thank you. No, there are people familiar with it. So it's header only, it's single header, it's boost license, there are no dependencies, it's all goodies. And it's compile time by default, but you can switch to runtime if you want. And it's not the boost library either way. It's just called boost, therefore the brackets. Just a disclaimer. OK, so as I pointed out, our code wasn't so scalable, in my opinion, because of this wiring and was pointed out by all audience. So let's try to make it more scalable with the containers. It might not, like a warning, it might not seem more scalable in the beginning, so just bear with me till the end maybe, and we'll see some benefits of it. So for example, when we have the speaker, so that's the implementation of object-oriented approach with hyperdynamic. We have to switch to the shared pointers because that's only what is allowed by it. So that's not good, but okay, we'll talk into that a bit later. So basically, we switch to the shared pointers. That's fine so far. And after that, we have this wiring in which we have the kind of builder. And that's the main part of all DI frameworks. It's basically when we want to bind some interface, some abstractions to some concrete implementation. So that would be like very common across all the DI frameworks. It's just a different, syntax, sugar. But the idea is that when we have the speaker, I want it to be the regular speaker. And that's all about it. Because DI frameworks, the good DI frameworks can inject, create the object graph, which doesn't depend on any abstract classes just by default. But if you have the abstract classes, we just have to tell the DI, well, this guy is actually, I care about the other guy. I want it to be that guy. Make sense? And after that, we build and resolve, and it will throw if it cannot be found. So about Google Fruit is very similar. It requires a macro to pass into your all constructors, which is not ideal. But well, we can deal with it, I guess. Although we have to kind of remember that DI is about reduced coupling, but we couple ourselves to the macro. Like kind of dodgy area, gray area. And it uses pointers here, and the idea is that we have the macro and everything else is as before. And the idea is that we create the component, bind the, again, speaker-like to regular speaker. We create an injector kind of thing, get the talk, and we can run it. So it's very similar to what we have so far. So moving on to the framework I introduced. So the good thing about it is we don't have to change the classes. So all of them are the same. We don't change the constructor parameters or anything like that to adjust to DI. It will deduce the constructors for us, which is good because it's less coupling. Less coupling is always good. And for the runtime, briefly, it's an extension because by default, the boost DI is compile time. But I just wanted to point out that it might be at runtime. We bind, nothing new, right? The two things to remember, DI, constructors, DI libraries, binding kind of thing. There's not much magic, and it will throw here when we try to create it. But with DI, we can also do it at compile time. So it's basically no different than before. Instead of extension, we just use auto, and that by default is compile time. And then the good thing about it is just if it won't compile, it means it won't compile if the binding is missing. So for example, if you miss the binding for the speaker-like thing, it won't compile and will try to give you a nice error message that you screwed up. So that's good. That's kind of scalable in my opinion because we don't have to bind all the things which are not related to the things which are abstract. There's a question?
Are those concepts as template parameters there? Or?
Right. So there's a really valid question. Are those guys concepts or interfaces, whatever, what that is, right? Basically. And we'll actually take a look into that, and that's actually anything. Might be a concept, or might be a concept name, or might be an interface. Yeah.
Maybe this was an unnecessary detail, but I didn't. Where does things like the speaker name? How does that get injected? That wasn't the detail.
Right. So sorry. It's a really valid question. What about speaker name and stuff like that? I just dismissed that for the sake of showing up those guys because it would have to be passed through here, for example, right? Speaker, or we could bind the first name, to something, last name to something, or we could just pass it here as a constructor parameters. There are options. So it's not like the I can't do that. I just didn't, focus on that. Oh, yeah, another question.
Can the database with two elements of, for example, speaker line, or we need to have only one one parameter with one concept or type? I mean, can they have two speaker line in constructor?
Right, so the question is whether we can have two speaker like in the constructor. No. We would have to bind it to in context, right? Therefore, the strong types are really good for DI, right? Because speaker like, it's not really that good a strong type. But if you have, it's maybe easier to think of it when we have the first name and last name, right? If you have the two strings, it's like you would have a string to whatever, and a string to is like which one is which one, right? So yeah, that's a valid point. That's not the strongest part of DI, but if you follow the strong types or context kind of thing, when you say it's like the first argument should be like that or something, then you can do it. So to sum up DI, the power of wiring. Let's take a look into that guy and remember that without changing it, we can actually go to a lot of concepts. So type erasure. So if you change the regular speaker to have kind of a functional approach, we could, and the wiring is the idea is that instead of talk we have the function call operator, and the main thing is that the same wiring. So the power of wiring with DI is the fact that without changing the wiring, speaker-like to regular speaker, we can create it so far with object-oriented design for the interfaces, and without anything changing for the type erasure std function. So I believe that's really valuable because then we can easily refactor the code, switch from interfaces to functions, and we don't have to change anything. The wiring mess doesn't exist for us because it's the same. It's the same for type erasure. So if you we used virtual concepts before, but it's like to implement that I used like some library, poly library. But it doesn't matter if you have the constructor being changed for these guys, the wiring is still the same. So that's the main point. It's like the wiring doesn't change. Speaker-like to regular speaker, attendee-like to awesome attendees, and the idea is that we just change our code the way we want it. So we say, I want that to be a type erase type, or that interface, or that a template, maybe. So a variant, the speaker-like in this case is a variant, and attendee-like is a variant as well. And what we can do, we can still create the talk with the same wiring. So the wiring doesn't change. So that's the main benefit of the DI frameworks, because we don't have to change the wiring and say how to inject things. We just say, we don't express how, we express what. And that's really declarative way of thinking, and that's really good, because DI will deduce everything around and just make it happen for us. And if we switch from variant to function, it doesn't matter. It will just create for us. And that's good. What about templates? With just a bit of change, when we put a name on it, so it's like kind of the default kind of parameter, the speaker-like here. So that's kind of referred to your question. So if the speaker-like was interface before, it was a class, and right now we just put a name on it, the wiring is still the same. So this time it's just a name, because it's a type, right? So then it will be the template will be the cpnow talk, which is templated, will be still created. With concept, we can follow the same approach and still make it happen. So the wiring is still the same. That's like, sorry, I'm repeating myself tons of time, but I think that that's very important to grasp that the frameworks, the main benefit of them is that the wiring won't change, and we get the benefits of being able to change different approaches without really dealing with the wiring mess. And that's what the frameworks are for. We want them to deal with that because we don't want. We want to do the business logic. Make sense? No.
On that side, is that supposed to say regular speaker and also attendees on the right? Otherwise, your speaker life is both concept and class in this declaration. And I don't see where the
That's a really valid point. I think it will collide. So let's say the speaker like concept. I'm not sure whether that will collide. Will that collide? Is it like forward declaration and a concept a problem? I don't know. Let's assume that this guy, it's called something else. But that doesn't really matter, right? Because like from the wiring perspective, we still wire it the same way. Sorry about that, and that's a really valid point. I think it will collide and it won't compile, but the idea behind it is still the same. So one point to consider, to remember here, is the fact that I pointed out that the wiring might be used for different approaches, which is good, and that's what we want, because when we're not coupled and we're not bored by doing the wiring mess. But it's often very, it's like if people pass the CMake thing with the DI, then they think that DI is only about object-oriented languages, and it has huge performance overhead, and it can't do templates, concepts, nothing like that. And that's not true. I think I tried to show that I think I've shown that it's not necessarily true that the containers can deal with concepts. They like DI. I didn't show that, but DI doesn't have any performance overhead. It actually can have and generate better code than handwritten manual wiring, because it knows all the types which have to be created, so it can create more cache-friendly layout, for example. So DI is good as a framework. And there are more benefits, and we all like benefits which are free, I guess. So refactoring with DI quickly. Let's change the constructor parameters, because that's the refactor we sometimes do, right? We change the orders, we add parameters, then new requirements. We deal with it and we change it because we have to. It will be a part of it. We'll have to change something. So these guys are all different because of something. So manual rewiring is refactor for money, basically, because we have to spend time and money doing it, because we'll have to change the wiring, right? Wiring mess, meaning construct it in a different way, change the order. So for the first one, you see it's like the second one is a bit different than the first one. It's a subtle difference, but we have to deal with it. It's like no one will do it for us. The order might be important. And again, if you think in large scale, that will burn us at some point, in my opinion. It burned me a lot of times. So with frameworks, we can actually just say create as before, because the wiring, the power of wiring is the fact that it deduces the constructor parameters for us. And it doesn't matter whether it's a unique pointer or shared pointer reference, it will deduce the lifetime as well and hopefully do the right thing. But the point is that if we even change just the constructor order, we don't have to change anything. It will just compile and work. And if we use the compile time approach, we even get a compile error if we screwed up. All of that is, in my opinion, good. For example, testing. We pointed out how to do the TDD with DI. It's like all of that is quite neat. With DI framework, we can do it even easier than before. So we still have the same code, and after that we just say make using some kind of mocks. So then DI for the unit testing can deduce, oh, that's an interface, or that's concept or type, and oh, I have to create a mock for that, and I can do that somehow. So for interfaces, there's like you can do the virtual table magic to make it happen, and for type erasure you can easily mock it as well. So there are options to mock it, and templates might be mocked as well automatically. So all of that is pretty good for testing. It's the same with integration testing. So let's assume you have this test, and you would like to change just a bit of the wiring for the like production code. We have the production wiring, which is like, hundreds lines of binding, but we have a database or something which we don't really want to integrate with in our integration tests. So we would like to change just that part. So what we can do, we can use the basic approach for the production injecting part sort of thing, where we bind everything the way we want in the production. And after that, we can just override something which we care to fake in our integration test. So like attendees maybe is not the best example here. We don't want to fake attendees maybe. But for example, if you want to fake the database or network or the time, that's like a logger, things like that. For the integration testing, it's like we just use the production wiring, and after that override something we don't want to use as the same as in production, and then we can have quite clean integration tests like BDD style. And the last thing is the quality enforcement. So it's often a case that you have like some different policies in the company that you would like to say, oh, we don't allow raw pointers. It's like we're better than that. So for example, imagine that, or something similar. We have like the talk3, which takes whatever that is. And after that, we have talk4, which takes a pointer to the speaker like. And we would like, since we control the whole object graph creation, we would like to say, do not compile if anyone passed the pointer through the constructor, because that's like against us. We don't know whether that's owned or not. Don't do that, for example. So then we can just introduce the policy. I don't point out how to do it, but it's very easy. We just say like, if it's a pointer, the type which is given, just bail out. And then we just get a compile time error for the guy which won't satisfy that requirement. So far, the talk 1, 2, and 3 will easily pass through because they don't have any pointers, and all the dependencies which are dependent on them. As I pointed out, the DI creates the whole object graph, so it's going through all the chain. So if you have one object and this object depends on other objects, DI will just deduce that and go like the whole object graph. But here, at some point, it will try to create talk4, and it will see that the speaker like is a pointer, and it will just bail out and doesn't compile because we didn't allow it to. So I think that's a good thing from design perspective, because we can write constraints of what we want. Make sense? So what's the point of all of that? I think the point is that, and I tried to convince you, I don't know whether I managed to do that, but the point is that we should consider using the frameworks to limit the boilerplate, especially when we do the large-scale development in which we don't want to deal with the wiring mess. Because otherwise, we will pay a lot. From my experience, at least, I will just share that with you, that spending time on dealing with wiring mess when it's huge, it's tedious, and it's not what I would like to do in my spare time. So if I can have a framework which will do that for me, I'm a happier developer, and I can be more effective in what I'm actually doing at work. But there are gotchas. So let's go quickly through that. So using container as a global injector, which is common, it's a common case. It's a bad thing. We don't want to do that. So because we go back to not having the constructors and having the kind of the singleton. Again, don't do that with the containers as well. Avoid that. So that's bad. That's good. Always pass what you need through the constructor. Service locator, that's really bad design pattern in my opinion. And the idea is that we couple ourselves to the service locator, which is just one constructor parameters, which just has to be passed through all the objects. And we always pass it, and then we resolve what we need out of it. So that's bad because we couple ourselves again to something which is DI related. Not great. So that's bad, but the passing speaker is good. And lastly, sorry, I'm going a bit fast. Maybe there are questions to the service locator. The idea is that we don't want to pass just one object through all the dependencies because that's coupling us to it. And we don't want to do that. Makes our life difficult because of the testing. Testing will have the God object kind of thing, which we have to mock all the resolve calls. And we won't be able to switch easily from DI, one DI framework to the other because we coupled ourselves. And lastly, we can couple ourselves to the DI framework, which is kind of mind-blowing, but we don't want to do that because DI is not all about don't couple ourselves, and after that, oh, but DI frameworks are cool, so let's couple ourselves to them. No, that's bad. So for example, with Google Fruit, we have this macro. The reason why we have this macro is like, consider not to do that, if you can. Also, Hyperdynamic has this subtle coupling in it, which is via the shared pointers, because it only allows shared pointers. So you have to pass shared pointers into all the constructor parameters, which is not ideal. Because, yeah, C++ is not about the shared pointers only. So the point here is let's consider not to couple ourselves to any framework. That's always good, because then we can easily switch from one framework to another, to the manual wiring. If we don't like the framework doesn't work for us. But then we coupled, so we can't switch, so we screwed, right? So that's bad, but that's good. So to sum up, because we don't have a lot of time, good practices are good practices for the reason. Solid is always better than stupid. Dependency injection, loosely coupled code, related, good. Easy to test code, good. Wiring mess, not so good. Libraries, promote loosely coupled code still, that's good. The wiring mess cleanup, good. Simplify refactoring with the constructor and stuff, good. Adding new features like the quality enforcement, good. Testing, even easier, good. Learning curve, not so good. We have to learn the frameworks, and there are gotchas with all of them, and even pointed out in this talk. So there are pros and cons. So just to sum up, the main part of the talk, because we have like 1 minute left. DI is just a fancy term for constructors. It's as I pointed out, it's a $25 concept for 5 cents term. It's very simple. If we follow, however, we can screw it up. That's another point. It can be easily misused, and it's often the case that, for example, we carry the dependencies around, or we don't do it right, or we assume that it has to be object-oriented design and stuff like that. So all of that make the DI really difficult to cope with when misused. So let's not do that. And I hope the talk helped a bit with doing it right. Important case, DI doesn't require a framework, container, library. We can do manual wiring as well. So DI concept as it stands might be used without the framework. Framework can help, but they are not required for achieving the good design which is flexible, testable, and scalable in the term I introduced it here. The framework helps with the wiring mess. That's good, because dealing with it might be difficult, and I pointed out that a few times. We always have to think large scale if it comes to that, because in the small scale kind of concept, maybe you won't see that problem, but in the large scale, it's probably a case. So yeah, we have no time, so let's just inject all the things, and thank you very much. I guess I can take questions, if anyone wants to. There's a question in the back?
Yeah, so
I should throw that, by the way. I was told to throw that, but I can't.
yeah, I can probably kind of maybe. So in like the small examples, yeah, DI has some things and constructors works great. And so I actually got super into DI like 2 years ago. Like I'm gonna do a project like following all the principles. And you end up in the situation where it's like, well, deep down in here I need like the logger, I need to access the like thread pool system, I need to access all these different things. And so up at the top you end up with, your wiring mess, you gotta pass 1,000 things down. And so then you're like, okay, cool, so I'll use a framework. Well, so you have this huge amount of things you need to pass to this framework, and let's say you have a large system, you're using this all over the place. How does this impact your compile time? Like, so I've noticed it's not exactly friendly to that. So it just makes using the whole concept really hard is what I've noticed.
Okay, so let me just rephrase whether I actually understood it. So the observation is that DI is fine and dandy, but may screw up the compilation times in general. So, well, I did the comparison of the BoostDI library versus manual kind of approach, as well as versus Java, and it compiles faster than Java, for example, which I find like the Dagger 2 implementation of the DI in Java. So I didn't see that problem. However, it might be slower, but I wouldn't say it's a blocker completely. Especially, well, at least with the BoostDI, I can claim that you can easily create. I have tests in which I create thousands of classes and ask it to create the object graph for all of it, and that compiles in like no time. But I see your point, and I see that since it's templated and it has to deduce stuff, and it's like a lot of TMP magic behind it, it might be an issue for some projects. So it's like, I can't give you a really good answer. It's like, I feel like it's not a problem, but I see your concern. It might be a problem. So it might be worth not to do it if you have that problem, right? It's always, depending on the case and the project. If that's answering your question?
Yeah.
Any other questions?
So one issue I've often faced is when working with a legacy code base, you're trying to do dependency injection somewhere further down the chain. And so you have this problem where you kind of have to pass the dependency 4 or 5 levels down the chain, or you have to refactor everything
Right.
up the chain, which kind of leads to my earlier comment of, now there's objects that need to know the dependencies of their dependencies, which is kind of a bad thing. And, per your advice, trying to avoid this, going to that object, as you called it, to get that dependency, definitely is easier, but
Right.
leads to other problems. And I was kind of curious if you tried to, had any experience with something like that in the legacy code base, and
Right.
what approaches you took to that, because I found that to be quite challenging at times.
Okay, so that's really a valid observation, and the idea is that the problem is that, especially in the legacy code, we may have code which is tightly coupled already, and we would like to switch to DI, but we cannot really easily switch to DI from the bottom up, in a sense, right? Because we would have to go to the composition route, and if we didn't design using DI from the scratch, well, that would be difficult because we have both approaches, and both approaches are never good. So my comment to that, because I've seen that and I deal with that for a while, we can still do it in steps. It's like trying to refactor towards the composition route and one place where we create all the objects. the first approach would be just to be able to create all the objects using like singletons or whatever with DI. So if you have the composition root which creates the, app or world, and it still is coupled, it's not ideal, but it can create it somehow. Then we can, we're already in a better, shape, because then we can change the dependencies one by one. But besides that, I can't give you any more advice. It's really difficult, and it's a long process, and it has tons of work to do the refactor from the legacy mode to kind of more modern world. But it's possible. I think it's possible, and I personally did it a few times, and it worked out when I approached it this way. So I could do the first step as I created with DI, but it's coupled. Like I don't have these bind calls for everything because it's coupled, because I use singletons, because I couple myself to like C code, and after that switch one by one as I go.
Maybe to summarize, it sounds like what you're saying is maybe okay to go to that
Intermediate
factory
state.
sense to get the object initially until you.
Yeah.
That's kind of your opinion.
Yeah, that's my
And
opinion.
that's where I ended up landing. You end up with this weird hybrid, right?
Right.
Some things are being passed, some are going to
Right.
the object to get it.
Yeah, it's a weird hybrid which you don't wanna deal with, but it's like that's your. It's really important, as I pointed out, it's like the changing the C testing framework to follow it through, because if you don't follow it through, you ended up with this weird state when you have sort of DI, sort of none, some sort of factory, some sort of manual, and then it's really difficult because it's not really easy to follow. But yeah, if you don't pass till the end, it will be difficult. I agree.
So one of the biggest problems I can see with dependency injections is sort of force away encapsulation. It reveals all of your internals of your objects and makes it available to the constructor. If I want to deliver sort of abstract classes to my clients, if I'm delivering libraries, so how do I both have dependency injecting for doing testing, but at the same time remove those constructors from my classes when I deliver the classes to other units of the company, so that they can just use the classes as they were originally intended to be used without any unit testing capabilities. Have any advice on that, or?
So the question is if I have, because I don't think that I actually haven't ever considered it this way, that you have different interfaces for the production and the and not the production code.
Just want nice simple interfaces for the consumers of the classes. They don't want to do all this wiring. They just want to say, I want this audit. And what the internal implementation is irrelevant to them. They don't want to know about it. But of course, for unit testing, I totally get the idea behind dependency injection. But it's incompatible for simple ease of use for consumers.
Well, I never thought about it this way. I feel like it's.
Imagine if standard string used dependency injection, for example. You want to do standard string. You got to then pass in all the internals in the constructor's standard string to create the standard string. That would not be a user-friendly standard string.
Yeah, but don't you just package up the Y plus your top level?
That's what I'm asking. What's your technique?
The higher level classes.
Yeah.
That's pretty much how
Right. So yeah, I think the concern here is really valid, but it's like what you expose to the user, it depends on you. Like as a library implementer who is using DI for my library, I can actually expose the only interface I'm interested in, and the details I'm not exposing. So for example, if I have an injector and I say the only thing which user can actually create is an app, they won't, the only call they will be able to do is create an app. They won't be able to create anything else, and everything else will be on the library side. So this way you would be able to get all the benefits of DI on your side, and the clients won't be exposed to that. So you can do that. It's definitely a valid point, though. But that kind of depends how to use DI, right? From library implementer perspective. My talk was more about user perspective, assuming that the library code is already there, and did that.
That breaking up also helps with compile a lot. Each subsystem is dependency injected, I guess. higher-level subsystems don't necessarily see everybody else's implementation details.
Right. So then, yeah. So the observation is that you can actually deal with fix the compilation times, but having, for example, CAP files for your library code, and what you expose is just one bigger type which users can consume. But all the details are in like CAP files, and you can test them using DI. Any other questions? No? Thank you very much again.